For as long as we've existed, we've looked up at the stars and dreamed, but they've always been just out of reach. The idea of actually crossing those cosmic oceans, I mean, that's the ultimate adventure, right? But it's going to take a kind of technology that's so far out there, it sounds like pure magic.
So, really, how do we pull it off? How do you build a ship that can jump between stars in a single lifetime? It's not going to be with chemical rockets, that's for sure. Even the most powerful nuclear engines we can dream up today just don't have the juice. The energy we need is, well, it's astronomical. The solution has to be something completely different. So what if we ditch matter as fuel altogether? What if we could build an engine out of the most fundamental thing in the universe, energy itself? Literally, an engine powered by a ball of pure, concentrated light.
Now, this isn't just some sci-fi fantasy. It's a very real theoretical possibility thanks to Einstein's general relativity. It's called a Kugelbitz drive, and at its heart is a starship powered by a black hole. Not one born from a star, but one we forge ourselves from light.
The word is Kugelblitz. It's German for ball lightning, which is a pretty cool name. The whole idea comes straight from the most famous equation in physics, E equals mc squared. It tells us that energy and mass are basically the same thing. And here's the kicker. Gravity doesn't just pull on stuff, it pulls on energy too. So if you can cram enough energy into a tiny, tiny space, you can actually warp spacetime and create a black hole. Okay, so let's get into it. How in the world, or I guess how in a solar system, would you actually build one of these things? The engineering required here is on a scale that is just, it's almost impossible to wrap your head around. All right, here's the recipe. First, you need the power of an entire star. That means you have to become what's called a Type 2 civilization and build a Dyson Swarm around the sun. To get the materials for that, you'll probably have to take apart a whole planet, something like Mercury. Then you use all that insane power to run a giant spherical array of gamma-ray lasers, and then you fire them, all at once, focusing a godlike pulse of energy onto a single point smaller than an atom. If you do it just right, the energy density gets so high it collapses under its own gravity, and poof, you've made a black hole. But you can't just make any old black hole. See, if it's too big, it doesn't give off enough power. But if it's too small, it'll evaporate in a literal flash of light before you can go anywhere. You have to find that perfect sweet spot. And that sweet spot has a very specific mass, about 606 million kilograms. To put that in perspective, we're talking about 600,000 metric tons. That's about the mass of a pretty decent-sized asteroid. And this is where the numbers get absolutely wild. You have the mass of an asteroid squeezed into a space of just 0.9 attometers. That is way, way smaller than a single proton. This tiny, tiny object would then blast out 160 petawatts. That's thousands of times the power consumption of our entire planet. And it would last for about 3.5 years. The perfect amount of time for a really fast trip to another star. So, you've done the impossible. You've created this tiny, absurdly powerful engine. Now what? How do you actually use it to push a starship? Well, you don't just use it. You have to ride the storm that it creates. You see, a black hole this small isn't black at all. It's white hot. It's constantly evaporating through what we call Hawking radiation, which is just a fancy way of saying it's spewing out this furious storm of high-energy particles in every single direction. And that storm? That's your engine's exhaust. But this exhaust isn't like simple rocket fuel. It's a whole mix of fundamental particles. A lot of it is quarks, gluons, electrons, and positrons. But as you can see, the single biggest chunk, almost half, is neutrinos. And that brings us to our first huge engineering problem. And here's the catch. Neutrinos are like little ghosts. They barely interact with anything. They'll fly right through your ship, your engine, you, me, the whole planet, without leaving a trace. So nearly half of your black hole's incredible energy is just gone. It provides zero push. Engineers have a name for this, the neutrino tax. It's a fundamental loss you just have to pay. So, to capture the other 55% of the energy, the useful stuff, the Starship needs a massive shield out in front of it. It's called a Dyson cap. Think of a giant concave mirror, probably made of titanium, that sits in front of the ship. The Kugelblitz hangs out in the middle, blasting away, and all those particles slam into the inside of the cap, transferring all their momentum and pushing the whole ship forward. It's literally like a sail catching this bizarre, super powerful wind. It's an absolutely incredible idea, isn't it? A star-powered laser making a tiny black hole that lets us sail between the stars. But there's a problem, a really, really big one, and it comes from a fundamental law of the universe itself. When we try to cram all of this unbelievable energy into one tiny point in space, does the universe just sit back and let us do it? Or does it fight back? It turns out you end up in a cosmic tug-of-war. On one side, you have our gamma-ray lasers trying to pour energy into a point to create a black hole. But on the other side, the very fabric of empty space pushes back with this really strange quantum trick. This trick is called the Schwinger effect. Basically, it says that if you make an electric field strong enough, the vacuum of space, what we think of as pure emptiness, becomes unstable. It will literally start to boil, spontaneously creating pairs of electrons and positrons right out of nothing. And that's the killer. The energy fields you need to create a Kugelblitz are way, way, way above that Schwinger limit. So as you're trying to focus all that laser energy, the vacuum itself starts to leak. It takes your energy, turns it into matter, and just flings it away, making it impossible to ever reach the energy density you need for the black hole to form. And this isn't just a guess. Recent research makes it pretty clear. This quote from a 2025 paper puts it bluntly. The Schwinger effect is basically a fundamental barrier. So here's the bottom line. Quantum physics seems to forbid what general relativity allows. The universe has a built-in safety valve that just might stop us from ever making a Kugelblitz. So, is that it? Is the dream dead? Well, maybe. But even thinking about this, the sheer scale of the ambition, it tells us something really profound about where we, as a species, might be headed. I mean, just considering a Kugelblitz drive forces us to imagine the roadmap to becoming a truly interstellar species. We're talking about mastering engineering on a planetary scale, taking planets apart for parts, building megastructures that can harness all the energy of our sun, wielding power on a scale that lets us play with space-time itself. The goal here isn't just about building a faster spaceship. It's about humanity graduating from a species that just lives on a planet to one that builds with them. It's about becoming architects of the cosmos. And that leaves us with this final massive question. Is the Schwinger effect a hard stop sign from the universe? A fundamental law that says, nope, you can't go here? Or is it just another mind-bending engineering challenge, one that's waiting for a breakthrough in physics so advanced that we can't even imagine it yet?